Welcome to lecture 18, which is on Newton's second law for rotation. In this lecture, we're going to talk about torque and about rotational dynamics. Okay, so let's talk about torque first. Okay, so imagine you're looking down at a door, okay? This is the top view of the door that you're looking at, and there's the hinge on the side. Okay, so let's say you're trying to open the door. So you try pushing it with the same force, but at different locations and at different angles on the door. So you have, first of all, you're looking down at the door, you push with a force, let's say this force over here, F2. Is that going to cause the door to swing in any way, open or closed? No, not at all, because you're pushing it in the direction towards its hinge, so it's not causing it to move or rotate at all. What about F4? Okay, with this force. So this force over here, now the magnitudes of all the forces are the same, but the locations and the angles that they're at are all different. So F4, what's going to happen to the door? You push the door over here with F4, it's going to cause it to rotate in this direction. So that's the counterclockwise direction. What happens if we apply the same force, but we apply it closer to the end of the door? So over here, F1. Okay, so the exact same force, but we apply it further away from the hinge. The hinge is called the axis of rotation. That's where it's rotating about. What will happen? We push it here, it will still move counterclockwise like before, but it's a lot easier to move a door when you push on near the edge away from the hinge than if you push closer to the hinge. So F1 results in a torque that's greater than the torque that's applied for F4. Even though the two forces are the same, it's easier to rotate the door when your force is farther away. What if we compare F1 to F3? Okay, so this time we're pushing with the same force, but it's on an angle. So we're not pushing it straight perpendicular to the door, we're pushing it on an angle. So what will happen? So F3 will still cause the door to swing in a counterclockwise direction, but it won't swing as quickly, or it won't accelerate as quickly. Okay, so the rotation will still be there, it will still be counterclockwise, but it won't rotate as easily. Okay, as if you were angling it straight on perpendicular to the door itself where F1 its direction is. So which of these forces would be the most effective at swinging the door open? That would be F1. Okay, which would be the least effective? That would be F2. F2 does not cause it to rotate at all. So torque, which is this symbol over here, measures the ability of a force to cause a rotation about an axis of rotation. Okay, so it's measuring the ability that a force is able to cause an object to rotate. So even though there is a force here, F2, it doesn't result in a torque because it's not causing the door to rotate. So here's the formula for torque. Torque is equal to RF sine of the angle, and I'll talk about what each of these means. So torque is equal to R first. R is the distance from the point of application of the force to the axis of rotation. So in case of our door, this is the distance from, if we're talking about, let's say F1, the distance from F1 to the axis of rotation, which would be where the hinge is, that would be my R. Okay, for F4, my R value would be smaller, it would just be this amount. Okay, so each force would have a different R value. So for F3, the R value would be the same as for F1. Then we have F, which is the magnitude of the force itself. So whatever the force is in newtons, that's what F would be. And then we have sine of the angle, and this angle is the angle between the force and the radial arm. So the radial arm means the vector that's drawn from the axis of rotation to where your force is. So here's my radial arm, looks like this, it's an R. Okay, so the angle between that and the force itself. So if my force is here, F1, so it's the angle between those two forces, those two vectors. So that would be 90 degrees for R1. Okay, so F1 has an angle, the sine angle, that angle would be 90 degrees. For F3 though, the angle would just be this angle over here. Okay, for F4 it would also be 90 degrees, and for F2 the angle would be a full 180. When you do sine of 180, if we think about what the sine graph looks like, it goes 90, 180, 270, 360, It goes 1 to -1. Sine graph starts at 0 and it goes up to 1, 0, -1, and back to 0. So sine of 180 is 0. So that's why when we put in 180 here, which is the angle for F2 over here, so that phi is equal to 180 degrees, and that, when we plug it into sine, we get 0. So the torque in that case is 0. And that makes sense because it's not causing the door to rotate at all. When the angle is 90 degrees, like it is for F1 and for F4, then sine of 90 from our sine graph is 1. And that's the biggest value it could be. So that's why when the angle is 90 degrees, we get the biggest torque possible for that force at that specific R value, that distance away from the axis of rotation. And then of course, the bigger the R value is, the farther away you are from the axis of rotation, the easier it is to rotate an object. So if the R value is small, like it is in F4, so this R value over here is quite small compared to the R value for F1, which is a lot bigger. The bigger the R value is, the bigger the torque will be. Okay, so there's a few things that cause torque to be big. First is the R value, so the farther away the force is applied from the axis of rotation, the bigger the torque will be. The bigger the actual magnitude of the force is, the bigger the torque will be. And then there's your angle. So your angle is going to be somewhere between 0 and 180. The closer it is to 90, the bigger your torque will be. So if it's 90, you have the biggest possible torque. If it's anywhere between 0 and 180, you will have a torque, but it's small when it's at 0. It's 0 when it's at 0, and when the angle is 180, it's also at 0. And when it's anywhere in between, it's somewhere between 0 and 1. This is the sine of the angle value. And so the closer your angle is to 90 degrees, the larger your torque will be. Okay? So here's another depiction of the same thing. So we have a force applied to the end of a wrench. This is the axis of rotation right here, which we can also call the pivot point. And the R value is this vector here that goes from the axis of rotation to where the force is applied. And the angle between those two vectors, that R value vector and the force vector, is your angle phi. Now it doesn't really matter whether we call it this angle on this side or this angle on this side. In the end, we will get the same answer. What will happen though is one will give us a positive and the other will give us a negative. And so what we do want to do is think about whether the rotation causes a clockwise versus a counterclockwise rotation. So by convention, if the force results in a counterclockwise rotation, we say that the torque is positive. And if it results in a clockwise rotation, then the torque is negative. Okay, so that's by convention. Of course, we can always use our own convention when we're doing questions, but this is by convention, just like we would say, up is normally positive, to the right is normally positive. But we can always choose our own convention if we wanted to for a question. Okay, when multiple forces are acting on an object, we can find the net torque acting on it by finding the sum of all the torques due to each force. But we need to keep in mind that our positive and our negative convention. So we might have a torque that's positive because it's causing a rotation that's going clockwise, and we might have another force that's negative because it's causing a rotation that goes counterclockwise. Sorry, I don't know if I mixed that up. We might have a torque that is positive because it causes a rotation that goes clockwise, and we might have another one that is negative. Oh wait, positive is counterclockwise and negative would be clockwise. It gets pretty confusing here. Okay, so counterclockwise is positive, clockwise is negative. So if we have multiple ones, then we would just be adding them up. We'd be adding positive and negative values together, depending on whether they cause the rotation to go clockwise, which would make the torque negative, or counterclockwise, which would make it be positive. Okay, so let's try this out. So we're going to draw a picture here. It says an 87 kilogram construction worker is eating his lunch at one end of a 16.4 meter long 460 kilogram steel beam. Okay, so here's our steel beam right here. And it is 16.4 meters long, so that's this distance here. And the mass of it is 460 kilograms. And so we have a construction worker that's on one end of the beam, and the other end is bolted into the framework of a new building. So here it's bolted in, so it's attached somewhere. Okay, so what is the magnitude of the torque about the point where the beam is bolted into place? So this over here would be my axis of rotation, because it's all rotating. The whole thing would rotate about this point if it was able to. So what is the torque about that point? So what we want to do is first figure out what are all the forces acting by taking a look at what the free body diagram would look like. So here we have an object, which is the construction worker, and he's eating his lunch at one end, and he has a mass of 460 kilograms. So then that means that he's applying a force of gravity that's pointing downwards. This is the force of gravity of the construction worker, or in other words, this is the weight of the construction worker. And so his weight, or his force of gravity, would be his mass of the construction worker times gravity, 9.81. So the mass of the construction worker is 87 kilograms times 9.81. And when I times those together, I'm just going to do that on my calculator. 87 times 9.81, and I get 853.47 newtons. So that's one force. Now there's another force here which is not very clearly stated, but because the beam has a mass, it's 460 kilograms, there's also a force of gravity, or a weight, acting from the weight of the beam itself. So when we put in a force from the weight of the rigid body itself, so this beam, we would put it at its center of mass. So at the center of this object, there's a force of gravity of the beam. So I'm going to call this FG beam. So this is just the weight of the beam, which is the mass of the beam times gravity. The mass of the green beam is 460 kilograms times 9.81 for gravity. And I'll type that up, 460 times 9.81, and we get 4512.6 newtons. All right, so these are all the forces that are acting on this beam, and so now what we want to do is figure out, well, what is the magnitude of the torque about the point where the beam is bolted into place? So we can look back at our formula for torque. So the torque is equal to RF sine of the angle between the r vector and the f vector. But we have two different forces here. We have a force of gravity of the beam and the force of gravity of the construction worker. So I'm going to put the net torque here, and so here I'm going to add up two different torques. So this is going to be the torque of the beam plus, and I'll call this B, I'll put little subscripts of beam. So this is all talking about the torque caused by the beam plus the torque caused by the weight of the construction worker. Sine of the angle of the construction worker. Okay, so we're trying to find the net torque here. So we're adding up all the all of the torques that are caused by the individual forces that are applied to this beam. Okay, so first one, we have our beam times force of the beam. So we're talking about force of gravity of the beam, which is 4,512.2 newtons. We're timesing that by the r of the beam, which means the distance from the axis of rotation to where that beam, or where that force is applied. So it's because we're saying that we're putting the force of gravity of the beam at the center of mass, it would be right in the center of the beam, which is 8.2 meters away from the axis of rotation, right? Because it's half of 16.4. So this is 8.2 meters. So my R of the beam would be 8.2 meters. My force applied there is 4,512.2 newtons. I won't put the units in here. And then I have sine of my angle between the r vector, okay, and I'll just draw in the r vector so it's clear. This is my r vector right here, and my force of gravity vector, so this vector here. So what's the angle between those two? The r vector is horizontal, the f vector is vertical, so the angle between them is 90 degrees. So we'd say sine of 90 there. Okay, so before we move on, we need to decide, is this causing a positive torque or a negative torque? Is the rotation going to be counterclockwise? That would be positive torque. Or is it going to be clockwise? That would be a negative torque. So let's think about this. If you have an object, I'll just redraw it here, and you push down on it over here, and this is the axis of rotation, is it going to cause the whole object to move clockwise or counterclockwise? It's going to cause it to move in this direction, right? All the way around like this. Well, what direction is that? That's clockwise. That's the direction that a clock would go. So that's the clockwise direction, and by convention, clockwise is negative. So we would put a little negative sign in here. Okay, then we do the next one, RC, FC sign of the angle for C. So C being the construction worker. So RC is the distance from the axis of rotation to the force applied for the construction worker, which is the distance all the way to the end right here, which is the full 16.4 meters, times the force applied by the construction worker, which is the weight of the construction worker, 853.47, times sine of the angle between that R vector and the force vector. Well, again, the R vector is horizontal, the force vector is vertical, so the angle there is 90 degrees. Okay, notice I didn't put a plus sign in yet because I need to decide whether this is causing a positive torque or a negative torque. So is the rotation counterclockwise or clockwise? So again, if I'm pulling down right here, I'm causing the whole thing to rotate in this direction. Okay, so that direction would be the clockwise direction, the direction that a clock would move. So that again is the negative by convention direction. Okay, so now we have our equation for torque, the net torque. So we found the torques caused by the individual forces that are there, and then we're adding them up. But because they're both negative, we're adding up negative numbers. So I can type this all up on my calculator. I get negative 8.2 times 4512.2. Sine 90, well, sine 90 is just 1, so I don't even have to type that if I don't want to. Minus 16.4 times 853.47. Again, I don't need to put in the sine 90 because sine 90 is just 1. And I get my torque is negative 50996.9, and my units for torque, so remember the R, that's a distance, so that's meters, and my force, that's a force, so that would be newtons. So I have meters times newtons, or you can just write newton meters. That's the more common way of writing it. So that's my net torque. The question asks for a magnitude, so it doesn't want to know what direction it's going. So we can say the magnitude of the net torque, so these lines mean magnitude, is the same value but positive. Okay, I'm going to look at significant figures here. There are 3 here. There are 3 here. There are 3 here because this decimal tells me that the 0 is significant in this case. So my answer should have 3. So 50996.9 would become 5. Well, the 09 would round up to become 10 times 10 to the 1, 2, 3, 4 times 10 to the 4 Newton meters. Okay, so that's question 1. Okay, question 2. Same idea. This time we have a wheel. We want to know what is the net torque on the wheel if the radius is 10 centimeters. Okay, it doesn't explicitly tell us, but the axis of rotation is here, the center of the wheel, because it's spinning at the axis of the wheel on the axle. Okay, so we have all these different forces here, and so I'm just going to label them all so that I know what's what. I'm going to call this one, maybe I'll call it this one, F1 is 20 newtons. I'll say this one over here is F2 is 30 newtons. I'll say F3 is also 30 newtons, and I'll say F4 is 20 newtons. Okay, so when I look for my net torque, then it's the torque caused by force 1, force 2, force 3, and force 4 all added together, but taking into account that some may be positives and some may be negatives. So let's put in the formula. So I have R1 F1 sine of angle 1, so meaning R1 is the distance from the axis of rotation to force 1, so that would be this distance over here, that's R1. F1 is this value here, the magnitude of the force, and then the angle, sine of the angle 1, that angle is referring to the angle between R1 and F1, so this angle here, which in this case is 90 degrees. And we'll do this for all of them, so I'm going to write plus R2, and this should say F1, not Fn. So I'm just going to erase that. That should say F1, sine angle 1 plus R2, F2, sine angle 2, plus, there's 4 of them, so I'm just going to keep going, all 4. F3 sine angle 3 plus R4 F4 sine angle 4. Okay, so now we just fill it all in. So we have R1, so R1 is the distance from the axis of rotation, which is at the center, to the point where force 1 is applied. So that distance, which is 5 centimeters, I'm going to change everything to be in meters so that our torque is in Newton meters, like the SI units say they should be. So 5 centimeters, I'm going to write it out as meters, so it would be 0.05 meters times F1, which is 20 newtons, sine of the angle 1. So angle 1 is this angle here we said, and that would be 90 degrees. Plus R2. Okay, so R2 is the distance from the axis of rotation to where F2 is applied. So that's this distance, also 5 centimeters, which in meters would be 0.05, times the magnitude of F2, which is 30 newtons, times sine of phi2. So the angle here is 45 degrees. So I'm going to write 45. Plus R3. So R3 now is this distance from the axis of rotation to the point where F3 is applied. They tell you the radius of the wheel is 10 centimeters. So that means that that distance there is 10 centimeters. Okay, so then if that's 10 centimeters, I'm just going to change that to meters, and I get 0.1 meters times F3. The magnitude of F3 is 30 sine of angle 3. So this angle over here, which is still 90 degrees. Plus R4. So R4 is the distance from the axis of rotation to the point where force 4 is applied. So that would be right here. That distance over there, that again is the radius of the wheel, so that's 10 centimeters still, so 0.1 times the magnitude of F4, which is 20, times sine of angle 4. So angle 4 is the angle between this vector, so this vector that we drew, and this vector over here. Well, they are really the same vector, they're pointing in the same direction. So whether we think of that as 0 degrees or 180 degrees, it doesn't really matter. Okay, because sine of 0 and sine of 180, both of them are 0, so it doesn't matter. Okay, so I'm going to put sine of 0. So this whole thing, sine of 0 is 0, so the whole thing becomes 0. And that makes sense, because if I pull on this wheel in this direction of F4, it's not going to cause the wheel to rotate at all, right? It's not going to cause it to rotate clockwise or counterclockwise, because I'm pulling it in a direction that goes right towards the axis of rotation, so it's not causing it to rotate in either direction. Okay, before moving on and actually adding up these terms, we need to decide whether each of these torques should be positive or if we should change any of them to be negative. So let's go back to each one and decide if they should be positive or negative, starting with F1 over here. So if I pull down over there, which way is my whole wheel going to rotate? I'm pulling down here, it's going to make it rotate in this direction. And what direction is that? It's counterclockwise, so that's positive. So we don't need to put a negative there. What about for F2? If I pull in this direction like this, which way is it going to rotate? It's going to make it rotate this way. And what direction is that? That's also counterclockwise, so again, that can stay as being positive. For F3, if I pull in this direction, which way is it going to cause the rotation to occur? It's going to make it rotate this way. And that direction is clockwise, and that's the negative direction. So this last term here should really be a negative, like that. And the final force, F4, is not causing a rotation at all. That whole term becomes 0, so we don't even need to worry about it. So now I can just take all these numbers, type them up on my calculator. 0.05 times 20 times sine 90. Well, sine 90 is just 1, so I don't even need to type that if I don't want to. Plus 0.05 times 30 times sine of 45 minus 0.1 times 30 times sine of 90. Again, sine of 90 is 1, so I don't have to type that bit. And I get negative 0.939. And again, my units are newtons meters. So find the net torque. So it's a negative 0.939 Newton meters. The negative implies that the wheel is going to be rotating in the negative direction, which is clockwise. Okay, so I can also write it as, I could also say, or a positive 0.939 Newton meters, and in brackets I could say clockwise. Okay. All right, so now we're moving along. We're going to talk now about rotational dynamics. So recall when we discussed circular motion that each linear variable in the kinematics equations have an angular equivalent. So delta S, the angular version of that was delta theta. Okay, rather than delta S being displacement, now delta theta is angular displacement. For the linear variable v, which was velocity, we have an angular version, which is angular velocity, omega. For the linear variable a, which was acceleration, we now have the angular version, which is alpha, angular acceleration. And then we talked about mass a little bit when we talked about moment of inertia. So mass was what makes it harder for something to accelerate. So remember we talked about F net equals ma. For a given F net, if we're trying to solve for the acceleration, it equals F net over m. The larger the mass is, the harder it is, or the smaller the acceleration will be. The harder it is to accelerate something. So as mass increases, the acceleration decreases, right? When you're dividing by a bigger number, you get a smaller value for your acceleration. So mass is what's making it harder for an object to accelerate. The bigger the mass is, the harder it is for it to accelerate, because acceleration will be smaller. What's the angular equivalent of that? Well, that was I, the moment of inertia. Remember, the moment of inertia depends not only on the mass. It doesn't only depend on the mass of the object, it also depends on the distance the mass is from the axis of rotation. Okay, so the bigger the moment of inertia is, the harder it is for the object to rotate. Then we have force, and that's where today's lecture comes in. So what was the angular equivalent of force? Well, that would be torque. Okay, so torque is like the angular equivalent of force. It's what makes the object rotate. Okay, so now we have the equation, which is Newton's second law, which is F net equals ma. Putting everything together, what would that equation look like in an angular form? F net would now become torque net torque, is equal to mass becomes moment of inertia, and a becomes alpha. Okay, so now we have a new equation. So it's the same equation as before, but the angular version of it. Okay, so let's revisit the wheel from question 2. If the wheel has a mass of 3.5 kilograms, what is its angular acceleration? So what is the alpha? Okay, so if we're trying to figure out what the angular acceleration is, we need to know how to use this formula here. If I were to write it out, net torque is equal to I times alpha. So we would need to know, since we're looking for the alpha, we would need to know the net torque and the I. Okay, so the net torque, we found it in question 2. So I'll just go back. Question 2, this negative 0.939, or positive if you say it in the clockwise direction, that is our net torque. So I'll write that down. So our net torque is negative 0.939, and the units for that was, if we go back, we can see them, newtons times meters. Okay, so we have Newton meters. Okay, so that's our net torque. What about our I, our moment of inertia? So for more moment of inertia, we need to go back to the previous lecture. Let me go back really quickly. We can see, you remember that we had a table here that showed the moment of inertia of different things. Well, what was the object we were just looking at? It was a disk. And the moment of inertia of a disk is right here, 1/2 mr squared. Okay, so let's go back to this lecture. The moment of inertia, it's a wheel, so that's in the shape of a disk, is 1/2 mr squared. Okay, so now we can figure out what all of that is. So 1/2, the mass is 3.5, and the r is the radius of the wheel. We can go back to take a look at what that was. The radius of the wheel was 10 centimeters, and its axis of rotation is at the center of the wheel. So we don't need to change the axis of rotation at all. It's already at the center of mass. Remember from the last lecture that if your axis of rotation is not at the center of mass, you need to use the parallel axis theorem in order to find out what the moment of inertia is from when the axis of rotation is somewhere else, okay, where it's not at the center of mass. Okay, so my r is 10 centimeters, which is 0.1 meters, and then that's all squared. Okay, so I'm going to type this up. I get 1/2 times 3.5 times 0.1 squared, and that gives me 0.0175. That's the moment of inertia. The units for mass is kilograms. For r, it's meters. So it's kilogram meters squared. Okay. So now we know the net torque. We know the moment of inertia. We're looking for the angular acceleration alpha. So let's rearrange our equation. Alpha equals net torque over moment of inertia. My net torque is negative 0.939 Newton meters. My moment of inertia is 0.0175 kilogram meter squared. And now I'm just going to divide those numbers. Negative 0.939 divided by 0.0175. And I get negative 53.7. Okay, it's alpha, which is angular acceleration, so my units are radians per second squared. Okay, what does the negative mean? I can rewrite it without the negative if I wanted to. 53.7 radians per second squared. It's in the negative direction, which means it's going clockwise. Okay, same direction as my torque. All right, question 4. So the figure below shows a piece of a large machine. There's a 10 centimeter diameter, 5 kilogram disc that turns on an axle. Okay, so you can see this is the axle right here. Let me change my color. The axle is right here, right there. Okay, that's the axle. The axle is the axis of rotation. That's where it's rotating about. Okay, notice that the axis of rotation is not at the center of mass. So we will, in this case, have to use the parallel axis theorem in order to find the moment of inertia at a point that's not at the center of mass. Okay, so it tells us that we have a 10 centimeter diameter, 5 kilogram disc that turns on an axle. A vertical cable attached to the edge of the disc exerts a 100 Newton force. So that's this force over here. It says tension. But initially, a pin keeps the disc from rotating. What is the initial angular acceleration of the disc when the pin is removed? Okay, so we see that there are 3 different forces acting here. There's the force of the axle, and there's the weight of the actual disc itself. And then there's that tension from the cable that was mentioned. So the first thing we can do is figure out what is the net torque. that's acting on this disc. Okay, remembering that the axis of rotation is at this axle over here. So we'll do the formula for net torque, which is R of the first axis, the first force. And so maybe we'll name all of these forces. I'll call this one F1, this one F2, and this one F3, just so we can number them. So we have R1 F1 sine phi 1 plus R2 F2 sine phi 2 plus R3 F3 sine phi 3. Okay, so let's find all of them. R1, so that is the distance from the axis of rotation, which is right here, to our force. So that's 2.5 centimeters. I'm going to change it to meters. 0.025 meters times force 1, which is that tension force, 100 newtons, times sine of the angle. So the angle between that r vector, this was the r vector, and the force vector is 90 degrees. So it'll be sine of 90. Sine of 90 is 1, so we can just rewrite that as 1, not even put it in. Now that torque there, that force, the tension, causes the whole wheel to, or the disc, to rotate in this direction here. Okay, so if you were pulling on this disc in this direction, it would cause it to rotate in the counterclockwise direction, which is positive. So we don't need to put a negative in front of that whole thing. Now we go to the second force. Okay, so this is the force of the axle right here. So we have R2. Well, R2 is the distance from this force to the axis of rotation, but the axis of rotation is right where that force initiates. So the R value is 0. The F2, it doesn't tell us what it is, but it doesn't even really matter now, because the angle between, because the distance from the force to the axis of rotation is 0, so there's no torque caused. So this whole term just goes to 0. Okay, so everything is just gone. So it doesn't make it rotate at all because it's pulling right at the axis of rotation. And then we do our third one, R3. So R3 is this force over here, which is the weight of the disc. And remember, we always put the weight coming from the center of the mass. So how do we find the weight? The weight is just mg. It even shows you right here. It's the mass times gravity. So that's the force of gravity acting from the weight itself. And it's a 5 kilogram disc. So our force 3 is 5 times 9.81. So that's what the force itself is. So we have R3, which is the distance from that force to the axis of rotation. That's this distance, which is 2.5 centimeters. So 0.025 meters times the force itself, which we said is 5 times 9.81. Sine of the angle between the two. So the r vector is looking like this. The force vector goes down like that. The angle between the two is still 90 degrees. So that just becomes 1. Now, how does that force cause the rotation? Is it causing a clockwise rotation or a counterclockwise rotation? If you pull down over here, you're going to cause the whole thing to rotate in this direction. Okay, because it's rotating about this point right here. So it's rotating around, that's the positive direction because it's going counterclockwise. So this is a positive value. Okay, so I can type all of this into my calculator to get my net torque. So I have 0.025 times 100 plus 0.025 times 5 times 9.81. And that gives me 3.72625 Newton meters. It's positive, which means it's going in the counterclockwise direction. That makes sense. Okay, so that's our net torque. The question is asking for the angular acceleration, so that's alpha. Alpha is my question mark. Remember, we had that formula that was Newton's second law, but the angular version of that, instead of F net equals ma, we have tau net, or net torque, equals, instead of mass, we have moment of inertia. Instead of a, we have alpha, angular acceleration. So we're looking for the angular acceleration, which means we need to know the net torque, which we just found, so that's good. But we also need to know the moment of inertia I. So moment of inertia. Okay, so this is a solid disk. It tells you we have a disk. It doesn't say anything about it being hollow. We know that it's not, like it shows that it's shaded in all here. So it's just a solid disk, and we can look at the formula sheet if we want again, just so that we remember where that's all located. We have a solid disk, that's this one here. The moment of inertia is 1/2 mr squared. Okay, so that's the moment of inertia of a solid disk about the center of mass, 1/2 mr squared. The mass of the disk is 5 kilograms, and the radius of the disk is the diameter is 10 centimeters, so the radius is 5 centimeters, so it'll be 0.05 meters squared. Okay, so let me type this up. I get 0.5 times 5 times 0.05 squared, and that gives 0.00625, and the units again, the mass is kilograms and the r is a distance, so that's meters, so it'll be kilogram meter squared. So that's the moment of inertia of the disk if it was rotating about its center of mass. Okay, so the formulas that you see that were on the formula sheet, those for the disk and for the spheres, those are all about the center of mass. But in this case, it's not rotating about the center of mass over here. It's rotating about the axle over here. So we need to use the parallel axis theorem to find the moment of inertia about a different location. And that formula was I equals I at the center of mass plus md squared. Okay, so quick refresher, let me just go back to that last lecture. Let me see if I find it. It's right here, parallel axis theorem, okay, just as a refresher. So we have the moment of inertia is equal to the moment of inertia at the center of mass plus md squared, where d is the distance from the center of mass to the new location where the actual axis of rotation is now. So let's go back to this lesson. So I have I, the center of mass, which I just found out was 0.00625, plus the mass of the object is 5 kilograms, times d squared. Well, d is the distance from the center of mass to the axis of rotation. Okay, let's clean this up a bit. Okay, so the distance from the center of mass, which is over here, to the axis of rotation, which is at the axle. So this is my d value, and it's 2.5 centimeters. So that's what I'm putting in for d. So 2.5 centimeters, I'm changing it to meters, 0.025, and that's squared. Okay, so now I'm finding the moment of inertia about a different point that's not at the center of mass. So I'm typing this up, 0.00625 plus 5 times 0.025 squared. And I get 0.009375. And again, my units are still kilogram meter squared. So notice that my moment of inertia just went up. It used to be 0.006 and now it's 0.009. It just went up. And that's because as the farther away your mass is from the axis of rotation, the bigger the moment of inertia is, because it's harder to rotate about that point. Okay, so now that we know our net torque and our moment of inertia, we can go ahead and use this formula here to solve for alpha. So alpha, if I rearrange, is net torque over the moment of inertia. My net torque was 3.72625 over the moment of inertia, which is 0.009375. And I'll just type that up onto my calculator. 3.72625 divided by 0.009375, and I get 397. This is alpha, angular acceleration. The units are radians per second squared. Okay, my torque was positive because it was going in the counterclockwise direction. My alpha is still positive, which means it's still going in the counterclockwise direction. All right, Next question, number 5. Okay, so for this question, we're going to revisit a common Pulley question that we've seen before in Lecture 11. But in Lecture 11, we were told to assume that the pulley was massless, okay? But now we're going to notice that when the pulley does have a mass, we're going to have to use rotational dynamics, which is what we're doing in this lecture right now to solve the problem. Okay, so when the pulley has a mass, the question gets a lot harder than before. Unless told otherwise, we're going to assume that the shape of the pulley is going to be a solid disk. So always assume that a pulley is a solid disk unless they tell you anything otherwise. Okay, for the apparatus shown in the figure, there is no slipping between the cord and the surface of the pulley. The blocks have a mass of 3 kilograms, the left one, and the right one is 5.7 kilograms, as you can see in the picture. And the pulley has a radius of 0.120 meters and a mass of 10.3 kilograms. Notice the mass of the pulley is given. That means you need to use rotational dynamics to solve this problem, which is what we're going to do right now. At the instant the 5.7 kilogram mass has fallen 1.5 meters starting from rest, find the speed of each block. Okay, so this point over here, this is using kinematic equations. We're trying to find the final speed, okay? And we know the distance that it's traveled, or the displacement, starting from rest, so we know the initial speed. What we need to do is find the acceleration first. Okay, so that's what we're doing in this question, is we're trying to solve for acceleration of these blocks, but because they tell us that the pulley has a mass, we cannot do it the way that we've done these questions before. We have to do it using torque, okay? Rotational dynamics. Okay, so what we're going to do is we're going to draw a free body diagram of each of the blocks first. So I'm going to start with the 3 kilogram block. Okay, so what does my free body diagram look like? So here's my block, and what's acting on it? We have a force of gravity that's pointing down, and I'm just going to call this one mass 1, and I'll call this one mass 2. Okay, so what is the force of gravity here? I'll say Fg is equal to m1 times g, right, because it's mg. And then we also have a force of tension. So this one here, I'm going to call it T1. Okay, so I have F1g over here, and this one is going to be F2g, and this one will be T2. So here I'll call this T1. And if I do the same thing, but this time for the 5.7 kilogram block, it will look just the same. I have Fg, so this one was Fg1, this one will be Fg2 equals m2g. And then we have still a tension, T2. Okay, so now which way is this whole thing going to rotate? Well, we know just by looking at it, the 5.7 mass is bigger than the 3.0 kilogram mass, so the whole thing is going to be rotating in this direction, right? So that means that the first mass, m1, the 3 kilogram one, is going to be moving upwards, and the 5.7 kilogram mass is going to be moving downwards. So the next thing we're going to do is write our formula for F net for each of these free body diagrams. But for the first one, the F1g and the T1, so the 3 kilogram mass, we're going to say the positive direction is upwards because that's the direction it's moving. So F net equals ma. But we're talking about object 1, so this is mass 1a. So what is F net for this free body diagram? If up is positive, T1 is the positive force because it's going in the positive direction, up. And then m1g, which is Fg1, is going in the negative direction, so it would be minus m1g. And all of that is equal to m1a. So now let's rearrange to solve for T1. So I'm just bringing the m1g to the other side. I have to change the sign, so it becomes m1a plus m1g. And then I'm going to do the same thing for the 5.7 kilogram block. This time though, The downward direction is going to be the positive direction because that's the direction that the 5.7 kilogram block is actually moving. So down is positive, F net equals MA, but this time it's M2A because we're talking about the second block. So what is the net force when we look at this free body diagram? In this time, the M2G is the positive direction. So we have M2G, and then T2 is in the negative direction, minus T2, because we're saying down is positive, because that's the way it's actually moving, equals M2A. Again, we're going to take this and rearrange to solve for T2 this time. So if we brought T2 to the other side to make it positive, and M2A to the left side, we'd get T2 is equal to M2G minus M2A. Okay, so I imagined that I took the T2 to the right side and the M2A to the left side, but then I just wrote it in the reverse order so that T2 was on the left because it looks better that way. So now we have our equations for T1 and T2. The next thing we do is we draw the pulley. So I'm going to write out, this is the pulley. So this is what my pulley looks like, and we're going to draw the forces acting on the pulley. So on the pulley I have a rope over here and I have a rope over here. So it looks like this, and here another one. So these are tension forces, and tension forces always pull, so it's pulling down on the pulley. So the first one is T1. It's the same tension that was pulling up on the 3 kilogram block is pulling down on the pulley, and then the other one is T2. Okay, so because the pulley has a mass and it has a radius, we're treating it like a rigid body. And what is the shape of a pulley? In every case, we're going to assume a pulley is a solid disc, unless they tell us otherwise, but it's almost always going to be a solid disc. Okay, so that's what our pulley shape is. So now we're going to look at the net torque of this pulley. So we're going to use the same equation we've been using before with F net equals MA, but instead we're talking about the pulley, which is a rigid body, which is rotating, and so instead of using the linear version of Newton's second law, F net equals MA, we're using the angular version, or the rotational version. So instead of F net equals MA, we're using net torque equals, instead of M, it's I, and instead of A, it's alpha. Okay, so I is talking about the moment of inertia of this pulley. So I'll put a little P here to remind us. This is the moment of inertia of the pulley. And alpha is the angular acceleration of the pulley. Okay? All right, so how do we find the net torque of the pulley? We have two forces acting on the pulley, T1 and T2. Which direction are we saying is positive? So normally we say counterclockwise by convention is positive, but in this question we've already decided which way the positive direction is. We said the positive direction is up for the 3 kilogram mass because that's the way it goes, and it's down for the 5.7 kilogram mass because that's the way it goes. That's the way it's moving. What about for the pulley? Which way is it rotating? It's rotating clockwise. So clockwise in this case is the way that we're going to say is our positive rotation direction. Okay, so you can choose whichever direction you want to be positive. I like making it the direction it's actually moving as the positive direction. Okay, so now if positive direction is the clockwise rotation direction, then which of the forces, T1 or T2, is making the pulley rotate clockwise in the positive direction? It would be T2. So T2 is pulling it in a direction that causes it to rotate clockwise, whereas T1 causes it to rotate counterclockwise. So T2 causes it to rotate clockwise, which is the positive rotation, positive direction, T1 negative. And it's only negative because I decided that positive is going clockwise for this question. Okay, so now let's find our net torque. Remember, it's R1 F1 sine of the angle 1 plus R2 F2 sine of the angle 2, and all of that is equal to I times alpha. Okay, so the I value is the moment of inertia of this disk. It's rotating about its center of mass, because pulleys will always rotate about the center of mass. Okay, and remember, the moment of inertia of a solid disk is 1/2 mr squared. That was on the formula sheet. So all of that is equal to 1/2 m, this is m of the pulley, r is radius of the pulley squared. Okay, because we're talking about the rigid body, which is that disk, the pulley, times alpha. Okay, so what do we know? R1 is the radius of the pulley, so that's R1. So I'm just going to write R for radius of the pulley. F1 is the force that's acting on the pulley over here, so that's this right here. Okay, so that's T1. And sine theta 1 is the angle from the axis of rotation to, so that r vector, the angle between that r vector that's over here, the r vector goes from the axis of rotation to the point where the force is applied. The angle between the r vector and the tension, that force vector there, is 90 degrees. So all of this is just sine of 90, which is 1. Same thing's going to apply for tension 2. This is my r value for tension 2. That was for 1. And the angle here is still 90 degrees. So sine of 90 is 1. So we don't need to worry about that. So R1, F1. So when we look at the tension 1, it's causing everything to rotate in a counterclockwise direction. And because we said clockwise for this question, we wanted to say clockwise was positive. That tension 1 is causing it to rotate counterclockwise, so we're saying that's negative. But when we do the second one, R2, which is still the radius of this disk over here, the pulley, times the force 2, which is T2, that one, that tension over here, when we pull it, it's causing everything to rotate in the clockwise direction, which is the positive direction for our question that we're doing right now. Again, sine of the angle is 1 because the angle is 90 degrees, so we're leaving that part out. Equals 1/2 times the mass of the pulley times the radius of the pulley, which is still the same radius here. So I'm just going to call it r squared times alpha. Okay. Next step is that the tensions that we got in the step above over here, these two tensions, we're going to put them in place of these two tensions over here. So we're going to take the M1A plus M1G and replace T1 with that in brackets. And we're going to replace T2 with M2G minus M2A. Okay, so I'm going to rewrite the equation but replace my tensions. So I have negative R T1, which is M1A plus M1G. Okay, that's from here. Plus R times T2, which is this one, M2G minus M2A, equals 1/2 mass of the pulley, r squared alpha. All right, so we're trying to solve for the acceleration. Remember, if we go back to our question, it's asking us to find the speed of the blocks after they've started from rest and their displacement's 1.5 meters. So in order to use kinematic equations and solve for the speed of the block, we need to find the acceleration first. So we're looking just for acceleration, not angular acceleration, but regular A acceleration. So that's this value here. Okay, but we have this value here for alpha, and we know there's a relationship between A and alpha. So what we're going to do is replace alpha with whatever it equals in terms of A. So do you remember we have this formula, A equals alpha R. So I'm going to replace my alpha. If I solve for alpha, I get A over R. So I'm going to take my alpha and replace it with this A over R. So this alpha over here is going to be replaced with A over R. Okay, and that's because I'm trying to solve for A, and I have this unknown value alpha here. And I'm trying to solve for A, but I have alpha, which I don't know, but I do know that alpha equals A over R, so I can replace it, and then I'll be able to solve for A. So let's do that next. So I have negative r m1a plus m1g plus r m2g minus m2a equals 1/2 mass of the pulley r squared, and then alpha is going to be replaced with a over r. Okay, so what happens now? This r squared that's over here and this r that's in the denominator can be partially canceled, so it can be reduced. The r squared becomes just r, and the r on the bottom goes away. But then what happens, we notice we have an r in every term now. We have this r, we have this r, and now we have this r that's over here. So we can divide everything by r. So when we do that, now all of those r's cancel out too. So this r is gone, this r is gone, and this r is now gone. So now I can rewrite my equation. So I'm going to distribute my negative sign into the brackets here because the r is gone. So I have my negative multiplied in. I get negative m1a and then minus m1g. And now I'm going to just distribute my plus 1. So that's not changing anything. I'm just going to drop my brackets. Plus m2g minus m2a equals 1/2 mass of the pulley a. And I'm trying to solve for a. Okay, so I'm just going to highlight all my a's. This is what I'm trying to solve for. So what I want to do is bring everything that has a onto one side of the equation, anything that doesn't have any a's in it to the other side of the equation. So let's do that. My terms that have a's on the left side are negative, so I'll bring them to the right side. So on the right side I have 1/2 m mass of the pulley times a. Then I'll bring this term over to the other side, making it positive m1a. Then I'll bring this term to the right side as well, making that also positive m2a. And on the left side, all I'm left with are the terms that don't have a in them at all. So I have negative m1g plus m2g. I'm trying to solve for a, so I can factor out an a over here, and I'm left with 1/2 mass of the pulley plus mass of object 1 plus mass of object 2. And on my other side I have negative m1g plus m2g. And now I can solve for a by dividing both sides by this bracket over here. So I have a equals negative m1g plus m2g over 1/2 mp plus m1 plus m2. Alright, so now I'm ready to finally put my numbers in. So a is equal to mass 1. So mass 1, if I go back to my diagram, mass 1 was 3 kilograms, mass 2 was 5.7. So I have negative 3 times g, 9.81, plus mass 2, which was 5.7, yeah, times g, which is 9.81, over 1/2 times the mass of the pulley. So I'll go back to the question just to make sure. The mass of the pulley, it tells us that it is 10.3 kilograms. Okay, the pulley has a radius of 0.120 meters and a mass of 10.3 kilograms. So it's 10.3 plus mass 1 again, which was 3, plus mass 2, which was 5.7. Alright, so I'm going to type everything onto my calculator. And I get negative 3 times 9.81 plus 5.7 times 9.81 over 1/2 times 10.3 plus 3 plus 5.7. And I get 1.91242 meters per second squared. Okay, this isn't my final answer, so I'm keeping extra digits. Now I'm ready to go ahead and solve the kinematic part of the question. It says, at the instant, the 5.7 kilogram mass has fallen 1.5 meters. So that's my delta S, is 5.7 meters. Let's go back. Oh, sorry, 1.5 meters. So my delta S is 1.5 meters. Starting from rest. So that means my V initial is 0 meters per second. Find the speed of each block. So we're looking for my V final. And I just found my acceleration, which is 1.91242 meters per second squared. Okay, it's asking for the speed of each block when the 5.7 kilogram mass has fallen 1.5 meters. So this mass, which is the one that is going down, has fallen 1.5 meters. We want to know, well, what is its speed right now? It wants to know the speed of everything. Well, the speed of the 5.7 kilogram mass is the same as the speed of the 3 kilogram mass. The 3 kilogram one is going upwards and the 5 kilogram one is going downwards, but they have the same speed because they're attached to each other with the same rope. Okay, so let's figure out what the speed is now. So we did the hard part for sure in the question, and now all that's left is a kinematic equation. Okay, so what equation are we going to use? We don't have time and we don't need time, so we're going to use the equation that doesn't involve time. So it would be V final squared equals V initial squared plus 2a delta S. So if we solve for V final, we would just square root the other side. V initial squared plus 2a delta S. So V initial was 0 squared plus 2a was 1.91242. And delta S is 1.5, all in the square root sign. And so now I can type all of this up. And I have 2 times 1.91242 times 1.5, all in a square root sign. And I get 2.395 meters per second. If I want to round that, I would get 2.40 if I wanted 3 significant figures, meters per second. And that is it. So notice how this question is significantly more challenging than questions we did before in Unit 11 when the pulley did not have a mass. As soon as you see that the pulley has a mass, you need to do it this a long way. So it's way more challenging when you need to involve rotational dynamics. Okay, so I hope that helped. I know it's probably pretty challenging and confusing seeing this the first time. That's why you want to practice this again on your own and do some of the homework questions. Make sure you understand this on your own because you'll have to do something like this on the test most likely. Okay, there's one more question in the lecture. I want you to try it out on your own and then watch the video. There's another video that's posted just for that one question alone. Okay, thanks so much for watching. I'll see you next time. Bye.